Welcome, everyone. Welcome to the Pearcey Foundation Australia 4.0 discussion series. My name's Wayne Fitzsimmons. I think I recognise all of you out there. We've been communicating a few times in the last couple of months, and I happen to be the chairman of the Pearcey Foundation. The Pearcey Foundation acknowledges all the traditional custodians who belong to the lands where the Pearcey Foundation and you, our guests, meet, live and work. We acknowledge the Aboriginal and Torres Strait Islander people with us today and their elders past, present and emerging, whose stories, traditions and living cultures in this country are a valuable resource, as are those of us all who have come to make Australia their home. Together, we are Australia. Good morning to you all, wherever you are in Australia or overseas. Welcome to today's final Australia 4 session, where we will be discussing some aspects of the critical digital technologies that will underpin the transformation of our national electricity distribution system. Australia 4 is an initiative of the Pearcey Foundation to recognise that in moving towards a net zero emissions in Australia, that transition of our electricity system to a decarbonised environment presents an enormous number of challenges. But with each of these challenges comes significant opportunities. Today, we're applying a particular digital and data lens when looking at the intersection of the electricity system with the ICT sector during this transition period. This series of discussions is targeted at bringing the energy and power industry sector together with the ICT sector to identify the challenges and the opportunities arising from this transition. We look forward to identifying some productive insights to benefit the whole of the community. And on October the 30th this year, we will be having a half-day summit to bring everyone together to consolidate those insights and learnings and to continue to move forward as a nation. We would like to acknowledge our sponsors, the Australian Computer Society, the University of Melbourne, Monash University and the University of New South Wales. Without their support, these sessions would not happen. We greatly appreciate their support along with that of all the speakers, as well as the organisations with which they are involved. Please note that this session is being recorded and will be published in a few days on our YouTube channel. All of the six recordings that have transpired so far will be available and are available now on our website. It's now my great pleasure to hand over to today's moderator, Professor David Hill. David received his PhD in electrical engineering in 1976 from New South Wales University of Newcastle. Since 2022, he has held the position of Professor of Electrical Power and Energy Systems at Monash University. He also happens to be the Professor Emeritus at the University of Sydney and the University of Hong Kong, and is also closely involved with the Office of the New South Wales Chief Scientist. His research activities have been in a diverse range of energy and power systems, control systems, and associated areas. His work is now mainly focused on issues for future energy and power networks, with the aim to help science accelerate transition to clean energy. David is eminently qualified to moderate today's discussions and introduce our three speakers. David.
Okay, thank you very much, Wayne. And well, good morning to you all. I'd first of all like to just simply compliment the Pearcey Foundation for organising such a timely series where we can actually focus on bigger picture issues in the energy transition. Not to duplicate what Wayne said, but there are challenges and opportunities that really can all benefit from digital technologies. And that's today's focus, critical digital technologies towards in the energy transition towards net zero. I will start. I'd like to say a little bit more about what I do, and but in particular to highlight the role of engineering and tech, and then Wayne's already described how the session will run, and but then I'll look back over the previous sessions and highlight two fundamental issues that could bring a bit of focus to our discussions, and then I'll introduce the speakers, of course. So as far as the opportunities go, I heard a Canadian professor now at Oxford some 10 years ago say that the smart grid agenda was potentially a business opportunity of $30 trillion. I'd love to hear what he would say now, given the energy transition. But it's certainly potentially huge. Okay, well, just a little bit more about me, because everybody brings a different lens to these discussions. I'm really an engineering scientist. My background, as I said, engineering and mathematics, and I've spent a career modeling and doing systems analysis, optimization, systems control, and largely for power and energy. And I've generally, I think, been focused on what could be rather than what is. And that's simply why I'm not retired now, because this is simply the most exciting period I've seen in power and energy in 40 years. But the systems area is the hard stuff. It's all equations and algorithms and complexity and so on. So I like to quote that two observations. The existing electrical system has been judged, I think, by the National Academy in the US as the most complex machine that humans have made. And electrification has been judged as the #1 achievement in technology in history by some organizations. So I think that gives us a hint that it's already pretty complex, and we're now trying to do it all over again on a much shorter timescale. So some of us old timers think that if people around now could really see all the problems that are going to come, they might be just a bit daunted. So this might be a situation where a bit of ignorance is helpful, and we'll just go ahead anyway. But I'm really confident that science and technology can solve any problem, just as it has in the past. But one of my pet ideas is that in Australia, I do think politicians, lawyers, and economists have had a bit too much say, and I think the engineers and technologists should get listened to a bit more. My PhD students get good jobs in AEMO and KPMG and so on, but you know, they're the guys under the hood doing the analysis. They're not speaking publicly. Meanwhile, industry needs a whole lot of new tools. We've got a big ARENA project to look at interactions between inverter-based resources across a large grid like Australia. We need new reliability and resilience measures and analysis tools. We have to analyze how the weather interacts with the grid. We need better planning tools. We need more flexible grids, and so on. So there's a huge role for engineering and technology. And that's why I'm, as I hinted before, completely delighted to be here where technology is uppermost. But I come back to the fact that I look at success in these areas through the lens of systems, interactions, control, decision and control. All right, as Wayne said, today's session, the format is pretty much as we've had previously. After my rambling at the beginning here, we'll have 3 speakers with about 10 minutes each, and then some Q&A. And a point to make is that the previous sessions have largely emphasized the challenges. They've put before us the things that need to happen, which of course gives challenges. The emphasis today is on how ICT can step up and facilitate solving these issues. So I'd like to just take another couple of minutes and highlight two things that I saw in the previous sessions that we could give a bit more attention to. So whether it's analyzing simulation of weather and scenarios for technology uptake and so on, which is an idea I got introduced to by the CSIRO actually as a participant in their Future Grid program, but talked about in our sessions by Jill Caney, on a time scale of years, whether we're doing that kind of analysis or, as John Fletcher pointed out, coming up with new control algorithms on timescales of milliseconds across the NEM. The fundamental thing that we need is to have the right data at the right place, at the right time, and in the right amount. Too much data as a control engineer is a problem. It's so-called cognitive overload. And if you start building models around it, you'll go down rabbit holes which are irrelevant. So I like the philosophical idea of, was it Occam's razor, where, less can be more. It's an idea that's used in art and science, and I saw recently in Victorian winemaking. So, so just the right thing at the right time, just big is not necessarily better. I liked Data 61's idea, or was previously NICTA, that data gives knowledge, which then gives decisions. So then that leads to discussions about who should know what and do what. And that's a distributed architecture for sure. So the issue here is that the energy sector is really reluctant to share data. It's a simple fact. You only have to talk around, and I see that as a major problem. Retailers own consumer data. Even the consumer, they own data that consumers arguably can't get access to. And the DNSPs need this data, and they have to either buy it or beg for it. So I probably shouldn't go on about that, but there is this reluctance to share at a time when we need the right data, and from households to the big grid. And there are various things limiting data. OEMs keep their control data to themselves. There's no actual public network models. And smart meters are only mandatory in Victoria and so on. And even then, the retailers own the data. The second big issue that I see, which many speakers raised in one way or another, was coordination. We have a nation build. I think Wayne mentioned this. We have a nation building exercise going on here, and it took 100 years to do the previous version. So it's got to be coordinated in some way. It's a simple control theory viewpoint, right? Otherwise, we get the tail of the frog. The frog gets in warm water and doesn't jump out, and we end up getting boiled. You have to know where you're going to be and make the trajectory there safe. Prices don't explode. People don't get thrown out of work unnecessarily, et cetera, et cetera. So I think these two issues are things that I can see we should give a bit of attention to. Okay, well, once again, I'm conscious of time. So let me just briefly introduce the speakers for today, who we're extremely pleased to have. First is Dr. Stephen Craig, who is the Smart Energy Mission Lead at the CSIRO. I believe that's a new thing. And he has a strong industry background in systems engineering, digital tech, and communications. Secondly, we have Dr. Sarah Goodwin, who's my colleague at Monash. She's a director of the Grid Innovation Hub, with a strong background in designing and improving visual communication of geographical and power network data. Certainly, it's great also to have Dr. Ian Opperman, who I used to know years ago at the University of Sydney, but he's now the Chief Data Scientist for the New South Wales Government. And I believe that's the only such position in Australia. And he's also an industry professor at University of Technology, Sydney. He has a strong background in mobile comms, AI, and digital economy. Their bios are on the website. And of course, you can easily find more detail about them at their organizations and LinkedIn. But I think here we have three experts who can give us different viewpoints from industry, research, government, and academia. So with that, I'll hand over to our first speaker, Stephen Craig.
Thanks very much, David. Let me share my screen. Is that coming through okay?
Yep, all good.
Excellent. So hi, everyone. Thanks for joining this session, and thank you again to the Pearcey Foundation for organising these important conversations. David asked us to each talk about two critical digital technologies in the context of power system transformation and perhaps more broadly energy system transformation. So I'd like to kick off the discussion by taking a systems perspective, sort of look at the large scale questions and how digital technologies can be important there. And then I'll hand over to Sarah and Ian to continue the discussion. So energy system transformation, power system transformation, more broadly, the holistic energy system, is obviously a major undertaking where success will not be achieved by new technologies, regulations, economics, environment, social considerations in isolation. It will be how all these factors actually come together as a dynamic and highly connected system that evolves over time. And it's an important insight because this is critical infrastructure. Obviously, it needs to operate as we transform it. So it's not good enough for us to just be sort of waving our hands around how this may all connect and work. We need a more stringent engineering-based methodology to ensure that these pieces actually do fit together and will serve society as we move forward. So that leads me to the first of my two critical digital technologies. It's actually a discipline, and it's the discipline of model-based systems engineering. And the model-based piece I will go into, that's where the key digital component comes in. So what is systems engineering? This is a definition from the International Council of Systems Engineers. Systems engineering aims to ensure the pieces work together to achieve the objectives of the whole. As a discipline, it originated in the 60s through the Apollo program to take humans to the moon and back safely. And my understanding is it's the only engineering discipline that was actually invented by practitioners rather than academics, because they had this need for all these different components and technologies required to successfully achieve that Apollo mission to actually work together. Things can go badly wrong without systems engineering. So here's an example from a railways scenario where the headline is unspeakable botch. Spain spends 258 million euro on trains that are too big for its tunnels. And you may think that this is from a long time ago. It's actually from February this year. Now, the individual technologies, the tunneling technology, fantastic. The train could be absolutely state of the art, but if they don't work together, we have a large problem. And I think there are analogies here in the power system, in the energy system, as we transform, that we need to make sure that these different components really do work together. So systems engineering's discipline to do that Model-based systems engineering is the contemporary way of doing it. So on the left here is the document-based systems engineering, which is where it started, obviously, through there not being the digital technologies that we currently have. That's certainly where I started my career in systems engineering. In communications, there were a lot of documents. And this is an aerospace example where you've got the different teams working on a complex engineering challenge, and there's a lot of rewriting of documents, translation of requirements, and it's difficult to manage because you've got these dependencies between the different documents, and there's no real single source of truth. The contemporary way to do systems engineering is model-based. It's digital, where you have a digital, visual, graphical system model that is the single source of truth for all the different groups working on the problem. And it has now become standard in sectors like defense, aerospace, communications, transportation. Has not been used as extensively in energy, but has an obvious role to play, we feel, in energy system transformation. It turns out that this is being done overseas. So one of the countries where systems engineering, and more specifically model-based systems engineering, is being utilised is the UK. They have a energy systems catapult organisation with a systems engineering team that is actually as large as their power systems team. I was visiting them in June in Birmingham, and I asked them about their recent work, and they referred to this report that has just been released last month by the UK Electricity Networks Commissioner, where they found through systems engineering methodologies that the length of time taken to build new electricity transmission from identification of need to commissioning could be halved. It was 12 to 14 years, but could be done in 7 years. And this surprised them, actually. They expected, maybe a 30% gain, but when they actually looked at all the different pieces and how it came together, they realized that you could probably improve this by a factor of 2. And I think that's a good example of the potential value of taking this holistic systems approach through systems engineering. So that's my first critical digital technology. The second one I'd like to highlight is maybe a class of technologies that under the umbrella of dynamic resource management. Now, we know that the energy system is being transformed to a system that is more connected, more dynamic, more collective, more distributed. So the cost of static worst case settings is just going to grow. So intelligence, dynamic resource management intelligence is becoming increasingly important. And I think we can see that in the context of AEMO's integrated system plan that you see an example from here, from the 2022 version, where the capacity in gigawatts grows through in different scenarios from 2023 through to 2050. The purple line at the top of the bars is the step change scenario that is often referred to as sort of the default scenario for where this may head. Some of the numbers there in the panel on the right about what this means, this step change scenario, are quite staggering. So an increase in storage capacity by a factor of 30 to 2050, a 9-fold increase in grid scale wind and solar, a 5-fold increase in distributed solar PV, and electricity usage from the grid to nearly double by way of example. That is an awful lot to be done in a short period of time. So utilization of our assets, our poles and wires and pipelines and various assets across the system will become really important because there is just so much to do in a short period of time. We have limited labor, we have limited materials. It's going to be really important that we get the most out of the system. And with the nature of the system, like I said, becoming more connected and dynamic, incredibly important that we have system intelligence here, and the ICT sector can play an important role. I will note that this step change scenario is not the only scenario. The hydrogen superpower scenario, where we go all in on building a green hydrogen industry and associated exports around that, implies a significantly higher increase in capacity. So if we look for that opportunity, the demands are even higher.
Wow.
Now, dynamic resource management, I think the ICT sector is really good at this. I worked in communications for many years as we were developing mobile communications. I remember back in the day with the 3G spectrum auctions and the eye-watering sums of money being paid for limited amounts of radio spectrum that really drove the need for spectral efficiency, so really efficient use of resources, and listed here were some of the areas that have been worked on by us at the time and then since then. Things like spectrum management, power control, mobility management, which I think will become important with EVs for the energy system as well, optimization of signaling, like the control plane, optimistic scheduling. So there's a parallel there, I think, to flexible demand, of being opportunistic when conditions are good, managing congestion, managing quality of service, and optimizing hardware and buffering through the system. And I think there's a parallel there to energy storage as well. Of course, the other key driver is that no one wanted mobile phone towers near their homes. And as we see today, no one really wants a transmission line near their homes either. So everything we can do to minimize the number of those, the amount of money that needs to be spent, and the sort of imposition on the landscape is going to be important. And certainly in the mobile communication scenario, we calculated that it was roughly a factor of 2 in terms of the number of towers we needed with and without systems intelligence. So there's a lot to be gained, I think, through this dynamic resource management and doing it well. So just finally, I would like to mention the smart energy mission that we're developing at CSIRO that David alluded to. It's focused very much on the energy system transformation as an integrated systems challenge. It's got 3 focus areas. The middle one, transformation, is about moving from this fossil fuels-based system to a renewables-based system, providing integrated analytical capabilities to help guide and de-risk those transition pathways. The foundation of the methodology there is model-based systems engineering that I mentioned. Digitalization, about enabling this secure digital intelligence to ensure we have efficiency and equity in future energy system operations. A big part of that is this dynamic resource management. The final area that I haven't touched on, but has been a theme throughout this series, as David mentioned, is empowerment, consumer agency. So this deep societal engagement to shape the future of energy to benefit all Australians, led by a social scientist that we're calling Empowerment. If anyone is interested in learning more about this initiative, do please reach out. We're currently developing and very keen to chat with people about the direction. And with that, I will stop there and hand over to the next speaker, who is Sarah. Thank you.
Thank you, Steve. Hope you all can see my slides. Thanks also to the Pearcey Foundation for this opportunity. It's great to be here today and be talking to everyone. As mentioned earlier, my research area is all about how do we visually communicate complex data more effectively. In particular, I have background in geographical data, and my focus is mainly on the energy sector and data-driven decision-making. I work from a human-centric approach. What does that really mean? Well, in the energy sector, it's vast. We have a wide range of stakeholders, or we could say users of data. This ranges from consumers to control room operators and everyone in between this. Data's everywhere, but it's not necessarily well used or effectively presented for those who actually need to use it to make effective and informed decisions. And as we move through this transition, data is becoming ever more important, more available to those who have access to it, and in a manner the manner in which we communicate it is really critical to ensuring that we can actually move forward. So what does the future look like? Yeah, I'm intrigued as well. Do we have future control rooms like this? Perhaps something like the movies with these fancy control rooms. But whatever the technical components here, notice that the people in the room are there. They're in the shadows, but they're really important in this digital and automated world. We can't rely on automation. Humans must be in the loop. They need to be able to interpret this. They need to be able to interpret the data and intervene when necessary. So data needs to be understandable, open, transparent, interpretable. We can't have black box solutions where they're not really communicated as to what's happening in the back end. The uncertainty in forecasting, for instance, needs to be much easier to understand and comprehend, so decision makers can make decisions based on the certainty of the data that they actually have to hand. So when it comes to our energy control rooms, we need urgent transformation. Our control room operators are already overwhelmed with the magnitude of information that they have to deal with every day. Effectively controlling the grid of the future with the current systems, in my eyes, is pretty impossible. We need to actually enable our expert operators to make more effective and informed decisions, especially during their critical periods where they're under stress. To do this, we can radically redesign these control rooms and improve the way in which we visually communicate the data, providing the right amount of information at the right amount of right time with the right context to make these decisions. What does that mean? Providing the right amount of information in a manner that's easy to understand. It's pretty harder. It's harder said than done. It means that we've got to understand what the operators are actually doing, designing for their needs, understanding what they actually need, and making sure these systems work well together. Lots of improvements that we can make. How do we know? Well, we have some evidence of this. We looked at our operators' cognitive load. It's pretty high during particularly critical periods. With AUMO, we've studied cognitive load of operations in energy control rooms. This we did as a non-intrusive study whilst they were working. We had eye tracking glasses, heart rate monitors, workload ratings, amongst other measurements that we were investigating. We studied over a period of 4 days, 8 different sessions, 1 hour each, where we were recording 2 operators at one time, and we were monitoring the situation and really trying to understand what was going on. This was covering training scenarios as well as normal control room operations. Basically, we collected a load of data to understand how people use data. Kind of ironic, but this is happening in all our research projects. Results indicate that many improvements can be made. Amongst other things, here we see current application layout is not optimal for the operator's task. This is eye tracking data from 1 hour session from one operator. On the left, we have the gazes, so what they're looking at on the screen, compared to on the right, where we have these trajectories of their eye movement from left to right. Color indicates direction. This is actually a shift change. After the shift change, the operators gaining situational awareness of the network after a few days off, after their shift. So you can see, well, whilst the 42% of the time was spent on screen 2, this is a single line diagram, the network diagram to gain awareness of what's happening. There's a lot of movement between the other screens, screen 1, 2, 6, and 7, a lot of back and forth. These long eye movements reduce our ability to retain the information. We can only hold a small amount of information in our mind at one time. So you've got to move back and forth to actually get this information if you need to reuse it and make decisions. So there's some evidence of wasted valuable time and effort here in this task, and we could really optimize the way in which these control room applications are designed for the task in hand. Obviously, it's easier said than done. There's lots of other tasks that need to be done, and we need to take those things into consideration, and each operator works differently. But this is just some evidence to start to understand why do we need to really understand what's happening in these control rooms and what is it that we need to change. Other than redesigning interfaces, there was a lot of need to things like automating tasks, making things possible to ensure that the operators are in the loop, but these things can be automated quite easily. there was a clear need also of a lot of different applications, each of them with their own different designs, lots of inconsistency in the way visual cues are used and audio cues are used. So enabling these systems to be integrated would be much more effective. Enabling and much more effective for the operators to make those decisions. There's also a need for operators to really communicate between each other. There's they communicate between two different control rooms. Of course, there's other types of control room. We have many different types, but communication is really important. Here, verbal communication is vital, but there's space here for the ability to use new technologies and start to have a much smoother and faster communication process. We've also witnessed this kind of these issues in other control rooms in different sectors. It's not just in energy, but here we can see that we can make some differences. There's need to really understand human cognition, data communication, social science side of things, as well as integrating with the engineering and of those who are actually building these systems. So there's a need for multidisciplinary approach here. Also, I teach thousands of students how to communicate data more effectively. These skills are coming into the workforce, but not many would be going into the energy workforce, and they're coming in slowly. We need to make sure that we get these skills into the energy workforce and start to look at training in this area. What other things can we do? Combine data more effectively. My area is geographical data, spatial data. I feel there's a real importance for spatial data in energy and communication. Historically, yes, it's been used, it's important, but it's still secondary to the network and the way in which the electrical network is structured. Our grid systems, as they transform and as we decentralize and as we have renewable resources, the accuracy of location information is going to be really important. Things like integrating weather predictions, ensuring that we have incorporated microclimates, for instance, is becoming important. And it means that our forecasts are going to become ever more complex. So we need to ensure that spatial data is integrated we can, there's lots of innovative ways of looking at this, and it's one of my favorite areas of exploration. We've got a few different projects that we've been looking at, simple little projects here, some student work where we've integrated a single line diagram of the Monash network together with a geographical map and used an more innovative approach of creating an interactive animated map and single line network together, and exploring with experts who need to use this information how this can be much more effectively used and combined. So that's one approach. I can probably jump on. You'll see this start to change and migrate from a network, a single line network, into a map and back again. Another project where we've been exploring the use of geographical data is actually using the underlying GIS data much more effectively. Here's a project where we use the road network and the building locations to estimate the network topology compared to an actual network. Here we can actually help to understand whether the digitization is good, and we can look at where we haven't got digitization, other countries where we haven't got this kind of information. I think there's some real need here to explore the use of the geographical data and combine it with engineers. We've been working with electrical engineers to see how we can combine this together to get a really strong result. So many projects in this space. Finally, I want to say that my whole research group, we look at embracing new technologies. This isn't about control rooms, but it's still about energy data. We've done lots of work on embracing new technologies, understanding how we can engage people in data, start to collaborate in a virtual world. This is a project all about the Monash microgrid and helping people understand data. And there's various projects in that space. Not to say traditional visualization aren't important. We still use dashboard designs, but we do make sure that we communicate information for the people who need it in a particular way. So this is all about the Monash microgrid, looking at microgrid climates, markets, and event performance. Thanks to, I didn't have just two things, I had lots of things to say, but really it's all about being human-centric and data-driven decision-making. Thanks to my colleagues, and I will pass to Ian, because I realise I'm over time. Thank you, to hear all about yours.
Thank you.
Thanks very much. And the analogies to mobile communications, I think, are really relevant in the world of energy. The difference really between the way an energy network works and the way a mobile communication network works. Energy networks move photons around that carry force. Mobile communication systems move photons around that carry information. But really, the evolution of mobile communications networks from being simple one-directional flows of information in centralized networks to multi-directional flows of information in highly distributed networks is a process of disruption that's happened with each of the Gs that we've had. We get a new generation of mobile communications approximately every 10 years. It's a little bit like Moore's Law. And we're currently living through 5G, 6G is planned for 2030. That disruption and that change of the way that value moves around the network in the form of information carrying photons is something that has fundamentally changed as those Gs have progressed. In the energy networks, we have moved from one directional flow of electromotive force from supplier through to consumer, increasingly to individuals in many different parts of the networks generating energy, and the need for the network structure itself to move from that one directional flow to a multi-directional flow where individual users will not only consume but also generate. Individual users will be prosumers in that network. In fact, many years ago, it was around about 2010, Nokia Siemens Networks at the time tried to take the operational support system, which ran mobile communications networks, largely 2G, 3G networks, and looked to adapt that for smart grids, creating a middleware layer that would bring about that prosumer idea, that multi-directional flow of energy into energy networks. Nokia Siemens Networks spent more than $1 billion trying to do that, and it was a complete and utter failure. And the failure was not because of technological capability. The failure was because the energy sector really wouldn't accept the idea or wouldn't accept some of the capabilities of mobile networks thinking. Mobile networks had moved to being not only able to take that multi-directional flow of information, but also do local optimization, create things around service level agreements, service level commitments, talked about customer experience management. At the time, energy networks were talking about users as load points. They were simply parts of the network which you consider to be part of an electrical circuit. That's where the energy went to be consumed. The other element, of course, about mobile networks is that there's been an increased use of data to personalize the delivery of a service. As a mobile user, you expect services to be delivered to you as you need them, as you want them. And part of that personalization increasingly relies on use of information about you as a consumer, where you are, when you are, what you're doing, what services that you're seeking based on the applications you're using on the phone. That in turn creates issues around personal information and creates issues around cybersecurity. Increasingly, the more elements of a network that you can expose information about you, your preferences, and of course, where you are and when you are, creates additional surfaces where that information can be captured by someone other than the network and be used for purposes other than for the benefit of delivering a customized service to you. By comparison, as we move to increasingly smart networks where energy is generated and consumed through prosumers inside that network, so people who both produce and consume, the ability to deliver customized services or deliver more increasingly personalized services requires use of personal information. David started out talking about smart meters and them being compulsory in Victoria. The moment anything smart comes into any network whatsoever, it starts to rely on information about consumption or information about preferences or information about when you are consuming. And all of that carries an element of personally identifiable information, revealing preferences, revealing information about you, revealing information about how you engage with the network. Similarly, cybersecurity issues start to become an issue when that personally identifiable or that personal information starts to be used to deliver those optimized services. And again, the potential exists for someone other than the network to take advantage of that information for different sorts of purposes. Where the energy sector has been going, of course, from a technological perspective, the functionality has been increasingly built into future networks, or built into networks as we start to accommodate that multi-directional flow of energy. But the equivalent of the privacy and the cybersecurity capability is far from sufficient to bring energy networks to the level of mobile communications networks. In the world of mobile communications, it's very heavily standards driven, and it's very heavily aware of the fact that it's not just about moving the photons of information. It is also about protecting personal information, protecting information from a cybersecurity perspective. Whilst the technical functionality for demand response and for the ability to start to accommodate the prosumers in energy networks is certainly moving at a pace, the equivalent of privacy and cybersecurity is something that really must be built into future standards for future networks. So David, with that, I'll pass back to you, but I think the analogies of what we've seen in terms of the self-disruption every decade of the mobile communications networks is the sort of thing that we really need to think about or use as a conceptual model when thinking about the necessary disruption of the energy networks in order to move to that point of highly personalized, highly adaptive and smart networks, which can accommodate our move towards net zero.
Okay, well, thank you all. That was great. So I look forward to some discussion now. I don't want to forget a question I've got in mind for Ian that I've added to my list. But so we'll go back to Stephen. I mean,
about to finish.
Sorry, Stephen, can you hear me?
I can hear you. Yep.
Yeah. Well, preaching to the converted on systems engineering, and oh my God, what a blunder, the train example. But you know, it's one. I mean, a blunder like that on a project, I would call it a project, you know, such as, you know, will happen in Melbourne and other cities around the world. Hopefully we get it right. But one of the speakers for one of the sessions talked about networks of networks, systems of systems. You know, ultimately our energy system, or the electrification, the electrical system, is becoming a bigger component as things hopefully get more electrified of an ecosystem of transport, water, weather, communications, and I'll probably forget one. And we need some measure of coordination across all these things. I use a study as an example. There was a study done by IEEE people, I think like 10 years ago, where they looked at all the major collapses. And in Australia, we're a little bit immune to this idea of a collapse, but other countries have lived with them. Well, of course, we had a big blackout 2016, but that fortunately, in some ways, alerted us to the fact that these things can happen. But I think they took the last 11 major collapses in the world and assessed that 10 of them were caused through poor communications. They basically looked at it as an interaction between the electrical network and the comms network. And the source of the problem was a stuff up in the communications. So that's just two networks interacting with each other. So maybe you don't have an answer, but I'd love to hear your comment on how we're going to cope with that complexity. Just to add a little touch to it, the previous market suspension, it's not talked about so much, but the interaction between the water network and the electrical network was huge. Like, we were dependent on hydro to keep the system up. It's a peaking power, but it was running all the time. And there was no headroom in the dams. So to get headroom in the dams, you need to release water, which can cause a flood. Anyway, you get my point. How do we coordinate across all that?
Yeah, great question. Obviously a real challenge, but you know, we don't have a choice. I think to your point, we need to do this, and we need to look at where there are methodologies and disciplines and examples where this is done. So if you look at contemporary systems engineering, model-based systems engineering, this has been developed specifically for these types of challenging questions that do cut across multiple domains and disciplines, and so on. And indeed, there is federated MBSE, federated model-based systems engineering, something being used. And if you look at other sectors such as defence, this is commonplace because you've got a very similar type of need for all these different disparate aspects to actually work together, where you can have cascading impacts. You can have threats that play out in one domain, but then flow through to others. So the work we're doing at CSIRO in collaboration with, for example, the Department of Home Affairs around the SOCI Act, Security of Critical Infrastructure, where they have these 11 sectors that are identified under the Act. A big focus of that is understanding the interactions and cascading impacts and resilience of this connected system. And I think model-based systems engineering does offer an engineering and an analytical methodology to address these types of questions that are very challenging, no doubt. In terms of how to go about the transformation, to Ian's point, I think we need to be much stricter on system architecture, interfaces, standards, because it's with that sort of structure you can actually contain this type of complexity. And I know Mark Patterson spoke to this in his earlier address around a layered architecture. There's and so on.
Yeah, he had, I think, seven layers. That was good. I just, before I go to Sarah, it's great. Thanks, Stephen. Of course, this is a period of time where the attendees can pile their questions into the Q&A. And after I've sort of done a little round of questions here to the panel, we'll try and bring some order to that and get some answers. So yes, please put your questions in the Q&A. Sarah, like this, I have two things that you could comment on if we get time. The first one is these centralized control rooms, which, I've seen pictures of my whole career. I even had a play in one once, which was a bit daunting to see the level of experience that these operators bring. So it's easy for me as an older person to really believe that we need the human in the loop, and that we don't want to hand technology totally over to ChatGPT and the like. But on the other hand, we've got self-driving cars coming along, which, look pretty good. They look even better than people in many ways. So this view of controlling the grid from a centralized control room with a human in the loop is something we're hanging on to. But I just wonder, are people looking at other, like this architecture question about where you distribute intelligence around? Should we have a distributed type control room with less emphasis on the central one? Or have you got a comment around that?
Yeah, for sure. I mean, I think that's why I put at the beginning where, what will the future look like? Technically, I don't know. But decentralized, absolutely, it makes sense as well. But I think, to me, what was really clear was the need for collaboration. So if it is decentralized, then we have different people connecting from different locations. They just have to be able to communicate effectively across those and be able to see. So certainly in those control rooms that we've been looking in, the connection between different control rooms was very important. So yes, they in a way, they're not necessarily just one control room doing all the work. It's others, and they're communicating, connecting with each other. Whether that's done effectively is yet to be explored, but certainly improvements can be made. Self-driving cars, I think we have self-driving cars. People are still skeptical. We still need someone at the moment in that car to intervene, and I think that's what I mean by having someone in the loop. At that, whilst we are whilst we can have automation, we can have some simple things happening, we can start to explore that. I think generally people are very skeptical, and so having them done in a way that we can intervene and that they can occur will start to make things easier, and hopefully we can move to a much more smarter system.
Oh, okay. I just want to inject a little bit of control terminology there. We talk about decentralized, meaning people act independently, but we use the word distributed for, you know, what's called message passing algorithms. You know, you have all these agents, and you need to work out who talks to who and who does what, and that doesn't need a central controller. So it seems like we kind of agree that that's maybe where things are headed. Although it's a little bit of a paradox, because we want coordination of the whole thing. So is that a paradox? Can we get all the different agents acting to make contributions in the operations area, like you've been talking about, but also in the planning area? And that's where I think it's coming unstuck a bit, right? I think we can sort the ops thing out, but the planning is a bit of a worry to me.
I mean, they're each different areas. Each of them, you know, we need to explore and understand what needs to be done to make sure that they're integrated. Certainly what I saw was, you know, things like solar farms, you know, doing their own thing, and having no one manning it. So and those in the control room, just, you know, there's no one to talk to. So it's very different from what they're used to. And, you know, there just needs to be a new way of doing that and making sure it's effective and much more, you know, smarter.
Okay, thanks, Sarah. I have another question around for an academic around universities and so on, but I might come back to that later.
Sure, no problem.
Ian, I loved your story about Nokia, and how, like, it's a sort of a fool's rush in where angels fear to tread story, I guess. But I guess you're saying they were a bit ahead of their time. They didn't realize the issues, the sensitivities, the different business models and cultures and so on in the energy area. But we're still in a place where, you know, even my grandchildren have these things, right? And we don't understand, you know, what's inside them, and they're purely functional, do what we want to do. But yet in the energy area, we have this distrust between the players to share data, and probably I would almost say some distrust on the part of customers, because they're not seeing lower prices right yet. They're not seeing, and the Victorians got upset when smart meters were added to their bills and they didn't really understand why. So what's going on? I mean, maybe this is part of your remit, I'm not sure, but it just seems to me there's just poor socialization of some sort, poor collaboration going on in the energy area. You know, after decades of inertia where everything was just the same, maybe it's expected. Like the comms area had these generations, and we're kind of used to that now. We're used to hearing of 4G, 5G, 6G, but in the energy area, we're not used to hearing this kind of thing. Yeah. So how do we fix that? And I guess I have another question for you, with just the role of government. I mean, I'm going to say straight up, I think they have to step in here somewhere. But I leave it to you to say what might be possible.
Thanks, David. There's a lot to what you just said. Let me try and go back to some of the earlier parts of what you're saying. Back in, it was 2009, 2010 that Nokia was doing this. It was Nokia Siemens Networks. It's now Nokia Networks. It's the bit of Nokia that's still alive, the networks business. When people looked at mobile networks and looked at energy networks, from a technological perspective, it seemed obvious that energy networks needed what mobile networks had. The planning and the optimization, it was really very sophisticated. The difference, of course, was that mobile communications had been around for a very short period of time by that stage, tens of years, 20 years. Energy networks have been around for hundreds or more years. And it's a very, very different mindset around energy networks. It's also a very, very different safety challenge. If your mobile phone breaks or your call breaks, you just redial. Whereas if it has something happens with an energy network, it's potentially life-threatening, or it could be lead to a natural disaster. And so the safety mentality and the engineering mentality was really quite different. But you can imagine a future where increasingly energy is being delivered, it's still being generated at very, very high voltages and with very large amounts of power. We're still talking gigawatts of power. But increasingly, when it gets to the low voltage network, we are starting to talk about increasingly refined amounts of power. So that safety challenge is something that might well change over time when we think about distributed networks and the amount of, if we talk about 5 kilowatts sitting on 5 kilowatts sitting on top of your house. So it's still in the realms of needing to be treated seriously from a safety perspective, but it's quite different in terms of the quantum we're talking about. And potentially, if we talk about microgrids, where you're running very, very small amounts of, you're generating very small amounts of power, again, we might start to see really those orders of magnitude change, and the local final stage of the network might start to look more and more like a network from the perspective of optimization and planning. So there's that. But you can imagine a future world where I decide I want to change my provider for my house, but I've got my electric vehicle, I've got my privacy settings, I'm prepared to trade off a little bit of personal information in order to get lower prices. I'm prepared to trade off a little bit of personal information to ensure that I switch on at the lowest possible cost time during the day. If I wanted to change providers with my mobile phone, I can, or if I want to change the phone or the provider, I can simply do some sort of update from one to the other. It's a little bit cumbersome, but it's not too bad. My profile, my settings, my personal settings, all just map across to my new device. Imagine doing that with your energy provider, where all the settings for my house and my car and all my preferences just suddenly swipe left and my house is updated, my car is updated. That's technically possible. And it's the sort of thing that people might start to expect because everything else in our lives is customized, is personalized. So it's the sort of thing that we could imagine for a future grid, and we could imagine, again, those different orders of magnitude between the voltages and the power levels in different parts of the network. But the challenge is, what is happening is policies being set around electric vehicles, policies being set around emissions, policies being set around what we're doing with renewables, without all the pieces coming together. And one of my genuine concerns, which I've voiced occasionally and had really interesting responses, my concern is no one's got this. No one truly has their arms around the problem, which talks about the emerging technologies, the current capability of networks, and the interaction between these now really complex multi-directional flows of energy inside a network, and energy and information parts of the network coming together and the cybersecurity parts coming together. I think generally government has to take a coordinating role. I think there's no other body that can do this. Government sets mandates around safety, around discrimination, around appropriate use of data. And I think the government has all the domains of relevant responsibility to say, you know what, this has to be a coordinated activity through government. Having said that, government cannot do it by itself. Industry can't do it by itself. Academia can't do it by itself. Standards can't do it by itself. All of those groups need to work together for the benefit of the consumer to deliver safe, reliable, affordable energy. And it's the reason I'm participating in this series of roundtables and ultimately the events in October is because I think it's really important to raise the issues and to help people who've always thought like engineers to think also like energy or power engineers to think a little differently. For governments to understand that a simple policy around electric vehicles, which looks like a really good idea, comes with incredible implications for the underpinning technology and the safety and reliability and stability of networks. This is something we all need to work together, but I genuinely believe government needs to play a coordinating role.
Great. Well, there's a few things to follow up there, but I think we'll turn to the chat and just see what's arrived. But thank you for those comments. Just looking along, whoa, this is a tough one. I've got, how do we measure something like intelligence or flexibility? All right, I pass on intelligence, but on flexibility, my point there was simply that the old grid paradigm was of fixed pipes, you know, going from big generators out to consumers. Now we need a network more like the comms network, actually, that it could be reconfigurable. Like that at distribution, we have an element of this already, but I've had a couple of students working on like we need to be, instead of building a network which allows for the maximum power transfer from a certain place, we need a more flexible network. Now, what that design looks like, I'm not sure, but that was my point on flexibility. How we measure it, I guess these are things that we need to work out. Okay, of course well, it's okay, there's various comments here. One person is commenting on the track record of South Korea and Australia in the comms area. I can't really, do you know anything about that, Ian?
I must confess that what I've looked at around the world in terms of energy networks, there are people who are doing it better than others. But I think this is an issue which everybody is struggling with, and good on South Korea for taking a more forward-leaning approach. Of course, South Korea is also home to a lot of telecommunications, mobile communications thinking and engineering, so it's not surprising that some of that's leaking across into other domains.
Okay, well, from Chris, I have it appears to be the most basic, totally unsupported premise that the Internet of Things must be the basis of grid control. One of the sessions had a talk on this, and of course, I guess it plays against the idea of some sort of customized architecture to some extent. But Sarah, can you see this question, and have you got a comment on that?
No, but I also agree there was a session on Internet of Things. I also agree that yes, sensing and basis of grid control most likely. The comment is interesting because it's talking more about PSTN, so linking it with the telco communication. I assume this comment came in during Ian's talk at the end, but yeah, interesting. I don't know if Ian can see the chat. This chat's hard to navigate a little bit.
Yeah, okay, there's a comment here from Jeremy Harkins. A rarely noted aspect of complexity is that as complexity increases, quality decreases. Well, do I agree with that? Not necessarily. I mean, certainly potentially, but it's how you manage the complexity. Sometimes complexity is like a forest, but if you find a couple of pathways through it, you're all fine. It's about complexity for me is about how many control parameters you need to get a result. The fact that something looks complex, like a large power network, doesn't necessarily mean, there's a problem. But if you need 1 million control agents to control it, then we've got a problem. So complexity, yeah, but there's no doubt we are in a more complex situation. We are moving towards bidirectional and flexibility must improve considering. Yeah, I think that these are comments. The point's made, flexibility needs to improve. Actually, I see these issues, controlling complexity, system resilience. These are the new buzzwords in infrastructure generally. And so the problems that we face are also there in other areas. Okay. Well, this is from Sarah. How about community sharing of energy driven by sustainable how much are we embracing technology to drive energy inefficiencies here? I'm not sure I understand the intent. Is Sarah available to elaborate on that comment? Okay. A lot of people are talking about complexity. What this means in terms of complexity, quality, digitalization is trending towards the other direction of increasing complexity. I just come back to my point. I'm confident that the right digital technology can fix problems, but as Ian commented on, as Sarah's commented on, and Stephen, we just have to get the right mix, the right coordination, and not have lines of, like I talk about in cybersecurity, the system now, everything from a smart meter to the large IBM computer holding data is a potential point of vulnerability. So that those questions, the questions of architecture and protecting data, using data where it's needed, can overcome complexity. I really believe that, as people have pointed out in other areas. I'm just sort of seeing if there's anything really that can fire us up here. I mean, somebody agrees with Ian, so I'll be pleased to hear that. So let's focus on that. Matt Peterson's asking, the information age works because there is convenient benefits to consumers. There is value for them. And one of the speakers back in the sessions brought that focus. I think it was from Earn Energy. And anyway, the idea that ultimately, what is the problem? What is the problem we're trying to solve? So some people think it's climate change. Some people think it's looking after the customer, making sure the consumer gets the absolute best deal possible, and so on. So, but the point of view is that what's in it for the consumer? The progress of the energy industry must introduce levels of consumer benefit and value. Change en masse will not be really accepted without consumer benefits. I mean, it's a good point. Consumers are only going to take for so long energy promises of energy prices coming down, and the reality being that they're going up. Okay. Oh, somebody else agrees with Ian. That's great. You're getting votes here, Ian. Karen is talking about the consumer focus. That's good. We need to keep, Jordan is saying, we need to keep perspective that Australia is not behind. Indeed, much of the world are looking to Australia. Yeah, I've heard the expression, we're like the living lab of energy transition in the world. I mean, of course, Denmark's done great, but they're connected to Europe. We're on our own. We're an isolated big island dealing with the energy transition with a whole lot of unique features. Abundant renewable power, long distances, so on. So looking to Australia as leading the way in the migration to renewables, the opportunity here is for Australian ICT innovators. So really good comment there. Very optimistic. Okay. All right. Well, one just with a few minutes, I had one or two other questions, and one of the concerns that I've already alluded to is just having the right workforce for the energy transition. I keep hearing, like integration engineers. I told a story the other day that one of my colleagues at the University of New South Wales is an expert on integration. So getting renewable power, batteries, whatever, connected to the grid. Coming back to Ian's comments about having the government processes to the hoops you need to, the right hoops you need to jump through to get connected. A lot of people think there's too many of them. They need to be better coordinated, but I'm sure that can be done. But this guy was teaching the hard equations type stuff about getting a big battery connected on the grid, training people. Then he figured out that he could make more money as an integration engineer himself. So he retired from the university. So I see that as integration engineers +1, but maybe -50, because a key educator has seen that he can do better actually doing rather than teaching. Now, some of that goes on, of course, but yeah, the training of people from, like, I was encouraged to hear from a DNSP recently that they've revived their apprentice program. I mean, in a big way. And by the way, their star apprentice was a young lady for electrician. So the whole workforce, I guess people are analyzing this, but certainly at universities, we are rethinking how graduates should be educated, and once again, maybe government can help here. And then on universities generally, I think it's true to say we feel a little bit left out in Australia of the whole conversation. We're kind of struggling to get in on the sides that the ARC, you go to all this trouble to put in ARC grants and get a whole lot of feral reviews, and basically some of us get it and some of us don't. And
I have a fish for Ludo having here.
Sorry, we have an interaction. So I invite questions on workforce, the role of universities. Maybe Sarah, you have a comment on why, am I right that we struggle to get involved in some ways? And I visit universities overseas, like in Strathclyde and Zurich and Denmark and so on. They have huge teams with huge projects funded with industry, doing lots of innovation on the energy transition. And it's hard to see how that could happen here in Australia.
I think it's happening. Whether we've got huge teams, no, I don't think we've got huge. We've got a lot of work happening, smaller teams. I think I agree. Large teams, connections, making sure it's industry focused, working together with industry, really, really important. Just to make sure that what comes out of the research is has immediate impact and can be used. So I think, yes, it's happening. I don't think it's happening enough, and I would love to see more coming in. And to me, research grants in this area, they're complicated. They take a long time to get, we can't wait for that to happen. So we need to make these things happen faster and working together to make that happen. In terms of training, it's something I've been talking about. I feel, yes, we train graduates, they go out and they go into the workforce. For instance, working in as an operator is not particularly appealing for a data scientist or maybe not even for an engineer nowadays. So it's something that we have to look into. We need to ensure that actually these jobs are appealing, and that the workforce is looking to see how the new graduates are actually what they're learning. But I also feel the opposite. We also need to make sure we train professional training. The universities actually work together with the industries and develop professional training that actually makes sense and we can all learn together. It's something that I've been looking into. We're looking at it at the moment, in fact. So love to hear what the industry really needs.
Yeah, there's, I think Georgia Tech in the US has a huge suite of courses available for industry. So I just wonder how they got.
We do it. It's just not integrated enough, right? In terms of having a suite of systems and really connecting it back to those who really are looking for it. So yeah, it's happening, but not to a big degree like some of the other universities.
Okay, Ian, Stephen, any comments on the role of universities and training the workforce of the future?
I can say a couple of things on workforce. I think the recognition that the energy system has looked sort of structurally pretty much the same for a very long period of time means that a lot of the people working in this industry have never seen this type of change before, and we've made the analogy to other industries like communications that have gone through multiple changes in these generations. So I do think there's a real need for these transferable skills from other sectors like ICT to be working with energy folks to get the right mix of skills needed for what we have embarked upon now and have ahead of us. So that's important. Just on the role of Australia, I think there's a real opportunity for Australia. What I hear is, we're at the forefront in many ways of the move to renewables. We're quite a nice size if we compare to trying to sort of coordinate America.
Or Europe.
or Europe. And we've got great natural resources, both renewable resources, critical minerals, and so on. So it's if anywhere in the world it offers the preconditions for coordination and actually moving forward on some of these key questions, I think we're certainly one of them.
Yep, good point. Ian?
My 2 cents worth. I think that it starts with awareness of the fact that we need to do things differently. And universities are wonderful in the sense that they have a degree of independent thinking, which they can imbue into their students. One of the things that I always do when New South Wales government takes on graduates, in particular graduates who are working or who come from ICT areas, is I give this big spiel about what government could be like. And most often the graduates stare at me and blink and say, well, isn't government already like that? And of course, the answer is no, it's not. And so carrying that attitude into the energy sector, into all parts of the energy sector, I think is really quite important. Helping undergraduates and postgraduates understand that we could do things differently. We don't have to keep doing it the same way, I think is a really important role of universities. But if we get the regulatory settings right, then I think we have a real opportunity to innovate in this space. There's so much innovation needed because some of the answers to the big questions haven't been invented yet. So if we've got the policy settings right, if we've got the environment right, if we've got the attitude right, there's no reason why Australia can't really innovate new technologies and new approaches, which could then be exported to the rest of the world, because this is a global challenge.
Great point. If it's any help here, I'm participating in conversations at the University of Sydney and Monash where we're kind of rethinking what education do people need to support the energy transfer. Unfortunately, it's too much. Like, it's hard to have a student understand the inner workings of a electronic converter and also appreciate complex grids and then the economics and how markets work and AI. How can AI help? So it's a big agenda, but yeah, we have to go beyond just thinking of it as power engineering or economics or all these isolated subjects. I think we're getting very close to the end of the allotted time. So unless anyone's got a burning question, I might move on to the final stages of our session. Okay, well, so with that, I simply, Wayne, you'll have the last word, I assume.
Yes.
But for me, I really thank the panelists for engaging so well with the topic. And I think we've had a good discussion, kind of at a fundamental level, really, which I always find refreshing. We don't necessarily have all the answers, but we've certainly raised some good questions. Behind the scenes, Karen and Colin have done a lot to keep us organised and on message. And once again, Wayne Fitzsimmons for the overall organisation. As Wayne will talk about, the culmination of all this is a summit and communique to come about in late October. I should also, well, Wayne's already thanked the sponsors, but let me do my bit too: the Australian Computer Society, the Uni of Melbourne, Monash, and UNSW. And yeah, finally, thank you to all the attendees. Over to you, Wayne.
Thanks very much, David. I would just like to recognise Jan Corwable, whose face has been on all 7 sessions, I believe, and she's from Perth, and she's been up very early. So thank you very much, Jan. So just to wrap it all up, we've had 7 sessions, and I've been most informative and quite diverse, which is what we were trying to do. We're going to present a communique at our summit session, but what we've done is we've got the transcription of the audio for every session, and we're using a version of ChatGPT to try and summarize those, because it's such a diverse series of positions taken on different topics. We hope that will work out quite well. So our summit is on the 30th of October in Sydney at the Sofitel. Registration will be soon available on our website, and we'll be emailing you for sure. There will be a small charge because we just got to cover our costs for that day, and we're having the Pearcey National Medal and Hall of Fame and Entrepreneur Awards that evening at the same location. So our goal at this summit is to present a plan for how we might approach 2024 and how we might, as an industry, come together. This was referred to during today's sessions. We're very fragmented, and we have to, as a nation, come together. And these sessions have demonstrated there is a lot of goodwill out there. So we're looking to bring Pearcey to bring ACS universities. We've had significant support from WESA, Engineers Australia, Standards Association, the energy centres in Monash and Melbourne University, all of the universities, of course, and some government involvement, although they're pretty reluctant, but we do all know that somehow they are going to have to get involved and somebody has to assume some role. I would just point out that, excuse me.
Leave it. Don't go back to it.
So it's the ACT submission from our Pearcey colleagues in Canberra have put in, for instance, an end user charging approach for high rises in the ACT, where they're going to be at 50% penetration of EVs in a very short period of time. Causes untold problems. But I don't think that's a problem we're going to have in metropolitan big cities, because there's a lot of other things to come ahead. So I'd like to conclude by saying 30th of October, Ian Opperman will be the moderator. We're going to have a great day and get some outcomes. It'll start at 9 a.m. on the 30th. Thanks to my colleagues, Colin and Jennifer, who are both on this show, on this session, to Jordan Green, who's behind the scenes with Karen in making all of these things logistically work, and to all of the speakers, in particular the 3 we've had today. So on that note, thank you very much for your participation. and I hope you found it worthwhile for these 7 sessions, and look forward to seeing you on the 30th of October. Thank you very much.